Okay, this is section 1.2/1.4 notes to try to get us caught back up for where we're supposed to be on our schedule. So 1.2/1.4. This is pretty much concerned with radicals, rational exponents, which are fractional exponents, and rationalizing denominators. So we're going to go through and work through these notes to, like I said, get us caught back up where we're supposed to be, and just more on a better path for getting where we need to be next week's classes and take the quiz when we're supposed to take it now, which has been shifted. Do remember that I posted an announcement that the quizzes have been changed from the original calendar. So first of all, you have to make sure you know what an nth root of something is. Most people know like a square root of something like 64. Square root of 64 is positive 8 because 8 times 8, or 8 squared, equals 64. When you're dealing with square roots, this is understood to be a 2 here. That means we're looking for a pair of something that multiplies to give us this. If we're dealing with cubed roots, we're looking for not a pair, but a triplet. So we're saying what times itself 3 times makes 27? And the answer to that is actually positive 3. When dealing with odd roots like cubed root or fifth root, sometimes you'll see things like a cubed root of a negative number. It is okay for a cubed root to have a negative number underneath because that would say, okay, if I multiply 3 negatives together, they're going to stay negative. So the answer to this is actually negative 3. Where we get into trouble is when something like this pops up. You can't say that the answer here is negative 8 because negative 8 squared is not negative 64. It's positive 64. So for us, until we learn what an imaginary number is, we can't do any even roots of negatives. So for us right now, we just say that's no real number or not a real number. So that's kind of what this little definition here with all these terms and things is trying to walk you through. It always makes a little bit more sense when you look at it number-wise. Now we have some properties right here. If the root on the outside is matching the power either inside or outside, so they can put it in here or they can put it outside, then the answer to that is A. So square root of 5 squared is just 5. Cubed root of negative 8 cubed is just negative 8. Cube rooting and cubing at the same time cancel each other out. Now, it's very basic if the power is on the outside. If the power is on the inside, you have to be a little bit more careful about what's going on with the base. For example, the square root of 5 squared, that's 25, and then you take the square root and it's 5, so that still works. The cubed root of 2 cubed is 8, cubed root of 8 is 2. That still works. So as long as the base is positive, nothing changes about how we evaluate it. If the base is negative, we have to think, because an odd root, that's going to be okay. If you cube negative 2, that gives you negative 8. Cubed root of negative 8, well, you can have 3 negatives. That makes sense. That would stay negative, so that would be negative 2. An odd amount of negatives is going to stay negative, and that's okay. Fifth root of negative 2 to the fifth is also negative 2. If you have a negative underneath and you have an even root, things are not exactly the base. So notice every time here, we've essentially just canceled the two parts out and gave the base back. So square root and square cancel, you get 5. Cubed root and cube cancel, you get negative 2. That is not true when you have a negative base under an even root. If you try to cancel that square root and that square, you'd tell me the answer is negative 3. That's not true because negative 3 squared actually changes to positive 9, and the square root of 9 is positive 3. So if you have a negative base underneath an even root, we want to make sure we report that as positive. If you do not know what the base is, for example, if I have square root of x squared, if I don't know if x is positive or negative, to be safe, I know I want to cancel that square root and square out, but I'm going to leave my answer in an absolute value. What that tells everyone is that I'm forcing it to be the positive answer, because when you squared it, it would have ended up positive, regardless of what x was. So to be careful about what x actually is, we put it in the absolute value. Now, if someone was to tell you that your base was absolutely positive and you know that, you don't need to worry about the absolute value. So if I gave you square root of x squared and I say in the directions, assume your variables are positive, then you would just say x. The absolute value would be overkill. These are just some common misconceptions. If you have a square root with a plus between two different things, you cannot square root each individual part. It does not equal the square root of a plus b. For example, square root of 3 squared plus 4 squared, if you tried to cancel them both, that'd just be 3 plus 4, which is 7. But that's not true, because order of operations says we have to work this out in order. So this is 9 plus 16, which is 25. So it's the square root of 25, which is 5. So just be careful about trying to use rules incorrectly. You also can't even split this into two separate square roots. What is true, there is one property we do have that says if you have a square root of a times b and they're both real numbers, so they're not imaginary or anything else weird, then you can split it into square root of a times square root of b. So that property is true, but not for addition. Okay, so let's go through some of these. We're just practicing simplifying a radical. What that actually means, and they did say that the variables are all positive, so we don't have to worry about any absolute values here. What it means to simplify a radical is it means to find out if there are any perfect powers that are factors of the number or letters inside. So when we think about that, we have to say, okay, perfect powers mean whatever this root is. So since this is a cubed root, this would be 1 cubed is 1, so I'm going to write a bunch of perfect cubes down here. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and 7 cubed is actually going to be bigger than 320, so that means I can stop listing. 7 to the third is 343. So it's obviously not that guy. So what we just need to do is check to see which one of these is the biggest perfect cube that goes into this. If none of these perfect cubes go into 320, then we know that this guy is already simplified. So I would start with just working my way up. Or you could start at the top and work your way down. Let's do that. That actually might be quicker. So 320 divided by 216 doesn't go evenly because you get a decimal. 320 divided by 125 doesn't go evenly. And 320 divided by 64. So 64 is the biggest thing that goes into this one. And the way we break this up is using this property right here. We say that this is the cubed root of 64 times what did we get when we divided, which was 5. So notice this still has to multiply back to 320 when it's in this format. Cubed root of 64 is this number right here, whatever it was before it was cubed. So to put this in final simplified form, you take the cubed root of 64. Anytime you physically take a root and it works out nicely, the root symbol goes away. It's like you've answered the question. For this isn't a perfect cube, so it is still under the cubed root. Okay, so let's talk about for a second, what do you do if there is a variable involved? For example, I'm just going to take a little side journey over here. Let's do something like the 4th root of x to the 6th. Okay, when you think about x to the 6th, you would say, okay, that is 6 x's if I was to multiply them all out. When you have a 4 out here, that means you're looking for a pair of 4. In other words, you're looking for an x to the 4th or something that is a group of x to the 4th, like x to the 8th, because that would be 2 x to the 4ths. So I see that if I just highlight these 4 x's, I could actually rewrite this as the 4th root of x to the 4th times the 4th root of how many were left over, which was x squared. The reason I'm doing this is, again, I've broken it up into a perfect group and a non-perfect group, because notice there's not even enough x's in here to make a group of 4. So 4 goes into 4 exactly once, so that would just leave me with x, and I would still have a 4th root of x squared. Now, that's a cool way of visualizing it, is to actually say, okay, look, I'm breaking this down into my groups, and I think about how many does it take to make a fourth root. It takes 4. I break that into a group because that then would just be x, and then I have my leftovers. There's a quicker way to get to this. Notice that this guy on the outside is to a first power. If you just take the power root on the outside and divide it onto the power inside, notice 4 goes into 6 once. 4 times 1 is 4. You subtract to get your remainder is 2. The 1 is the power on the outside. The remainder is the power left on the inside. So you can do this just by doing division. 4 goes into 6 one time completely. That's why there's an x to the first on the outside, with 2 left over. That's why there's 2 inside. So let's see if we can use this trick of division to do part B. First thing I need to do is break down 16. The biggest number that goes into 16 without going past it would be 8. So this would be cubed root of 8 times cubed root of 2. So I'm breaking that apart. And then I'm just going to break these into individual variables. Now you could get really fancy like I did up here, and you could break it into a fourth root and a square, which for us we'd be looking for groups of 3. Or you can just do the division rule, which is what I'm going to do. So notice I've got a cubed root for each piece. Okay, so cubed root of 8 is 2. Can't take the cubed root of 2, so that's just done. 3 goes into 3 exactly once, so there's going to be an x to the first on the outside, and there were no leftovers, so no x's left inside. 3 goes into 8 2 times completely with 2 left over, because 2 times 3 would be 6, so 2 left over on the inside. 3 goes into 4 one time completely with 1 left over, so there'd be 1 inside. Your final answer on these is to take all of the outside things, the things that came out of the roots, and write them out front. So 2xy squared z to the first, and then all of the things still under the cubed root get put back together. So 2y squared and z. And then that would be my final answer in its simplest form. Okay, so let's look at this last one here. This has got times between it because there's nothing written there, so this is not a cubed root, this is a square root. To make my life easier, I think I am going to try to multiply this back together first and try to just look at one piece. So 3 times 6 is 18. A squared times a to the 5th would be a to the 7th. B cubed times b to the 1st would be b to the 4th. If you need to, write the little 2 here to help you remember it's a square root. Remember, perfect squares are 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and once you get to 5 squared, you've gone past 18. So the biggest number here that could possibly break down is a 9. So I would think of this as square root of 9 times square root of 2, because that multiplies to give me my 18. And then I'm going to be looking at a square root of a to the 7th and a square root of b to the 4th. Put my little 2's in here if it helps. Okay, square root of 9 is just 3. Square root of 2 does not break down. 2 goes into 7 3 times completely, so that would be an a to the 3rd on the outside with 1 left over. So that would be a to the 1st on the inside. 2 goes into 4 exactly 2 times, so that would be b squared. My final answer, I have a 3 on the outside, an a cubed on the outside, and a b squared on the outside. In my square root, I would still have a 2 and an a. So there's that one. Okay, so let's look at 2 more. This case, you have to be careful. The directions here say x and y might be negative. Why that's important is that means if you're dealing with an even root, you're going to need absolute value around your variables that come out of the radical. Sorry, trying to read and write at the same time. Okay, so notice this first one is an even root. So let's first of all think about the fourth root of 81, r to the fifth, and s to the eighth. Okay, so think about fourth roots. 1 to the fourth is 1, and you can use your calculator. 2 to the fourth is 2 times 2 times 2 times 2, that's 16. 3 to the fourth is 3 squared times 3 squared, which is 9 times 9, so that's 81. So actually, this guy is a perfect fourth, and his root is 3. So that's just going to come out as a 3. Because that was never negative to begin with, we don't need to worry about an absolute value on that. We don't know if r or s are positive or negative. So anything we pull out after this point, because this is an even root and they said they could be negative, we'll need to put that variable in an absolute value. So 4 goes into 5 one time completely. That's why I'm going to have an r on the outside in an absolute value. I'm going to leave a little space to see if I have any s's in there too. And then I would have 1 left over on the inside. So I'd still have a fourth root of r. 4 goes into 8 exactly 2 times. So I would have an s squared right here. Now, then you get into discussions of, does the absolute value truly need to be on both variables? If the part you pulled out is an odd power, it must be on it. If it's an even power, it's negotiable, because honestly, even powers will get squared or to the fourth power, and they'll turn in positives anyways. So this is fine for me. Like if we were in a testing situation, WebAssign may want you to distinguish that the r must be forced to be positive, whereas s squared is already going to be positive. So they may do that. They may only put the absolute value on the r. And we don't put this case on the test where it's possibly that it's negative. So this is really just something that if you were going on to a much higher math class, you'd be a lot more concerned with some of these details. Okay, and then this cubed root one, because it's an odd root, we don't need to worry about any absolute values. So cubed root of 8 is 2, 3 goes into 6 exactly twice, and 3 goes into 3 exactly once. There's not a radical left. Everything went in completely, so everything was a perfect cube. So let's talk about rationalizing next. That's the next piece. I'm not going to read you this property because that just confuses people. Let's talk about what is rationalizing and how do I figure out how to do it. If you want to rationalize a denominator, that means get a radical out of the denominator. That's what rationalizing really says. You could rationalize the numerator. That means you wouldn't want any radicals in your numerator. We don't usually go that route unless you're in like a higher level calculus class where you want to manipulate something so that the radical's in the bottom. And there are reasons sometimes when you would want to do that. For college algebra, we always rationalize out of the denominator, and so that's the same thing we do for trig as well. So how do you do that? Well, the way we do it is we create a perfect power in the denominator. And then we simplify. So what I mean by creating a perfect power, a lot of students remember rationalizing and they'll say, oh, you just always multiply by whatever's in the bottom. That's not always true. It is for square roots. It's not for any other roots always. So if I wanted to turn 5 into a perfect power and it needs to be a square root, since this is a square root, I want to turn 5 into a perfect square. The way to do that is to multiply it by another square root of 5, because when you have two square roots that are multiplied together, you can multiply the numbers inside. So whatever you do to the bottom of a fraction, you do to the top. So this becomes square root of 5 over square root of 25. The whole point of doing this is that this is now a perfect square. You don't want to try to reduce anything like on top and bottom. You want to just evaluate the bottom. So square root of 25 is 5. And I've accomplished getting that radical out of the denominator. I'm going to come back to B in a minute. Let's look at this C. If you have a radical that goes on top and bottom like this, it goes all the way across, you can actually split it into a radical on top and a radical on bottom. To get the radical out of the bottom to go away, we need to make 3 into a perfect square, since this is a square root. So we're going to multiply by square root of 3. On top, you'll get square root of 6. On bottom, you'll get square root of 9. And square root of 9 is actually 3. Be careful, do not get tempted to try to reduce the 3 and the 6. 6 is not really a 6, it's a square root of 6, which is actually a decimal. So outside numbers can only reduce with outside numbers. Inside numbers can only reduce with inside numbers. Okay, so in both of these cases, we did just multiply by whatever was in the bottom. That is not true when you have a cubed root or a fourth root or a fifth root, something different than square root. Notice this is cubed root of x to the first. If you want this to be a perfect cube, you will need 2 more x's. So to make this go away, you need to make sure that whatever's in here is a perfect cube. So if I multiply by x squared, I get cubed root of x squared on top because it's times 1 over cubed root of x cubed because it's x times x squared. And now that I made that add up to 3 overall as a power, that will then cancel out that radical in the bottom and leave me with just x. Let's look at another one. This is a fifth root. So I have fifth root of x over fifth root of y squared. Make sure you don't lose your fifth root there. We have y squared down here. We need it to be something that is, you kind of see a pattern here. It needs to be divisible by 5. If I could just throw in 3 more y's, I would then have a y to the fifth. Whatever you do to the bottom, you have to do to the top. So now I have fifth root of xy to the third on top because you multiply these together over fifth root of y to the fifth, and we just simplify that bottom. So that would just be y. Where you should be a little careful is make sure that none of these powers inside on top are bigger than the 5. If they are, that means the top can also have something pulled out. But everything inside is a smaller power than this root, so we're good. All right, let's look at this one. So I have square root of 3x, if I want to split it up, over square root of 2y cubed. I need to turn both the number and the variable into perfect squares. So to make the number a perfect square, you just multiply by another 2. This is a 3. Even roots need to have something that they divide into evenly. The first number that 2 will divide into evenly that's bigger than 3 is 4. So we just need 1 more y to create a 4. Now, if you did y to the third, that would work, but you're actually creating more work in the end product. You'd have to reduce more. So this would be square root of 6xy if we multiply across the top over the square root of 4y to the fourth. So square root of 6xy. Square root of 4 is 2, and 2 goes into 4 exactly 2 times. So I have a y squared on the outside of that. And then here's the last one of these. If it was me, I would take care of that negative power first. We don't have any rule that says how do you divide with negative powers. It's better that if everything has a positive exponent. And I'm not even going to split this one into 2 separate radicals on top and bottom because everything in here is a perfect square. Square root of 16 is 4. 2 goes into 8 exactly 4 times, so there won't be any leftovers. And 2 goes into 2 1 time. So that b is in the denominator. Okay, so this is jumping back to section 1.4 for a second because everything we did in the last examples right here all had a single radical or single piece of information in the denominator. Like even though there were 2 or 3 things sometimes in the bottom, it was one term with no adding or subtracting. Where things get messy is when your denominator is a binomial with a radical in it. So either one of the pieces is a radical or possibly both are a radical. The way we get rid of that is we can't just multiply by one radical. We actually have to multiply by something called the conjugate. Now, you've seen conjugates already. You just didn't know it. X plus 5 and x minus 5 are actually conjugates of each other because when you FOIL this, you get 2 middles that cancel out and you're left with just perfect squares. So we're using a conjugate idea, which means everything's the same except for the sign in the middle. That's what you change. So let me look at my example here. I have square root of t minus 4 over square root of t plus 4. I'm going to multiply by square root of t minus 4 because that would be the conjugate of this part right here. So conjugate means you write the same thing that's in the denominator, but you change the sign in the middle. Whatever you do to the bottom, you must also do to the top. Now, where this differs in the difficulty is that this now is foiling or distributing. So we have to do square root of t times square root of t, so that'd be square root of t squared, square root of t times negative 4, so negative 4 square root of t. Notice this negative 4 was not under a radical, and so therefore it stays outside, and the square root is where it's at. We also get another negative 4 square root of t, and negative 4 times negative 4 is positive 16, so that's my top. And yes, this does reduce, but I always do that after the foiling or distributing. Square root of t times square root of t is square root of t squared. Square root of t times negative 4 is negative 4 square root of t. Don't try canceling stuff because that would be illegal cancellations. 4 times square root of t, notice this is why we use the conjugate. Those are actually opposites and cancel out. And 4 times negative 4 is negative 16. For cleaning this up, both of the t squareds that are under the square root would just be t's. This would be a negative 8 because they're like terms on a square root of t. And then I would have my plus 16, so that's my numerator. You can't add these together because this is a power of 1 and this is not. This is a square root. On the bottom, this would just be a t, and then we'd have a minus 16. Now, here's where students sometimes get into trouble for elite, and notice there's no radical on the bottom. We completed the goal. You cannot cancel this t with this t or this 16 with this 16. When canceling something, it has to be in the same format. So if this is a binomial on the bottom, the only way you could cancel anything is if you had a matching binomial on top, or you were able to factor something into a matching binomial. So do not partially cancel in polynomials. Okay, so this leads us to the last topic from the section, which was 1.2 rational exponents. Essentially, this is telling you that when you were dealing with something like the cubed root of x squared, there was a different way of writing the same exact problem. And you think, well, why would I care about that? Well, sometimes being in one format or the other can be superior for solving or finishing a problem. So this is how it works. Whenever you have a root, you actually have an exponent, but the exponent is a fraction. The number inside is the numerator. The number outside, or the root, is the denominator. So this would be x to the 2/3. So this is just showing you that that property can happen a couple different ways. You could also have seen this like this, where the 2 was on the outside. That is still the same thing. So when you transfer like an exponent that's rational back to a radical, you can either put the numerator inside with the variable or on the outside with a parentheses around everything. Okay, so let's just practice a couple of these. So for this, we want to convert this to the exponent from the radical. So this would be x to the 3/4, and that's it. You've converted the format. For example 6, write these all back into radical form. Be careful here. This is why I point this out. In this first case, notice there's no parentheses, but in the second case there is. When there's no parentheses, the power only goes to the base directly in front of it. So this 4 is not included. So it would be a 4, and then when you write this as a radical, you look at the bottom for your root. So this would be a square root of x to the 3rd. Now I could simplify this, but they didn't ask us to simplify. It just said rewrite. So unless it says rewrite and simplify, you can just leave this alone. In this case, though, everything is being included because of the parentheses. So this is square root of 4x, and we usually keep this in a parentheses so that the 3 can apply to all of it. So 4x to the 3rd. In this case, something similar is happening. This one only gets the root on the x, whereas this root goes on the whole thing. So for this one, it would be 4 plus the square root of x to the third. And this one would be the square root of 4 plus x all to the third. So the syntax of how they've written it is very important, as is noticing whether or not something is in a parentheses. Which leads us to our last examples in this packet. So I'm thinking most of you in 1.2 have encountered these in the homework and you're thinking, she hasn't covered that yet. I'm covering it right now. And what we'll probably do when we see each other again is I will probably have a little worksheet, maybe a little longer than normal, and we'll spend some group time working through some of those problems to make sure everybody's good with this material. So this right here is something where you think, okay, how would I approach this type of problem? You cannot multiply these two pieces together. First of all, they don't even have the same base. And if they did, if they were both 4s, to multiply them together, you'd have to add the powers. So then you'd have to worry about having common denominators. What sometimes is more helpful is to think, would this be more beneficial if I changed it to the other form? I will point out that you really want to take care of this negative exponent before you do that, though. So I have negative 27 to the 2/3 power, and I'm going to move this 4 and its power to the bottom to take care of that negative exponent. So 4 to the 5/2. Notice it went from a negative power to a positive power now. So the first thing I would do is convert the top using our radical notation. So this would be cubed root of negative 27, and I am more likely to usually put the square on the outside, because remember, it can go either inside with this or on the outside. The reason I don't put it inside is I don't want to square negative 27 and then try to figure out a cubed root of a huge number. So the cubed root, and I've still got to do the bottom, so this would be square root of 4, and again I'm going to put that 5 on the outside. It's legal to put it either inside or outside. Cubed root of 27 is negative 3, but I still have to square it, and square root of 4 is 2, and I'll have to raise that to the 5th power. Negative 3 squared is 9. 2 to the 5th power, if you use your calculator, is 32. So this whole thing that looks so strange from the beginning actually works out to 9 over 32. Sometimes variables are actually more beneficial to deal with. You still have the power rules here. I can apply, since there's no adding or subtracting, I can apply the power on the outside to everything on the inside. So this would be 2 over 1. So this is just multiplying two powers together. Remember, power, power, you multiply. So this would be r to the 2/3 and 6 over 3. So s to the 6 over 3, which means that s is actually just squared. Depending on how they allow you to have your final answer, if they say you can use exponents for your final answer, which I didn't specify, this would be if they say just write your answer using positive exponents. If they say write your answer using reduced radicals, that means they want you to change any fractional exponents back to radicals. So that would make that the cubed root of r squared. And notice there's less r's inside than the root, so that is reduced. So this could be either way depending on the directions. Okay, only 2 more to go. Be careful here, don't try to multiply yet. This has a squared on this first one, so order of operations says we have to square everything here first. So 2 squared would be 4. This is power, power, so this is like a 2 over a 1. I'll rewrite that. So this is 2 times 2, which is 4, so I have an x to the 4 over 3 times 1, which is 3. And then I have to do the squared power down here as well. 2 times 2, 1 is 2, over 1 times 2 is 2. That actually just ends up being y to the first, because it's a half of 2. There's no power on the outside on this one, so I'm just going to rewrite it. And we're going to try to simplify what we have left. Okay, so if you want to write that guy as a 1, you can. The multiplication of the numbers is pretty easy. 4 times 3 is 12. When you try to multiply the x's together, you have to realize that x times x, you add the powers. So I'm just going to write what that would look like. I'm not done, I just have to write it out. So it's 4/3 plus negative 5/6. I'm going to have to simplify this exponent. And then the bottom would be y, again, y times y, so I'm going to have a 1 plus a 1/3. So I'm going to do a little scratch work. 4/3 plus negative 5/6. Need a common denominator, so I'm going to times the first fraction by 2/2. So 8/6 plus negative 5/6 is 3/6, or 1/2. So it looks like my top is 12x to the 1/2. And for my bottom, I have 1 plus 1/3. So you can write 1 as anything you want over itself. So 3/3 plus 1/3 would be 4/3. So y to the 4/3. And I'm going to leave it like this because if you turn it, the problem with this one, and why we wouldn't give you one like this probably on a test, is that a lot of students will be like, good, you let me leave it in exponent form, and you forget that this is actually a cubed root down here. So by our laws of rationalizing, that's technically not okay to leave it like that. But we don't worry sometimes about certain situations like that because it makes the problem really, really difficult. So if they want all positive exponents, this is actually okay. All right, and then this last one down here, we have a negative 1/2 power on the outside. Okay, so because it's negative, that kind of throws everything for a little bit of a loop. The quickest way to fix this is we can change this to positive if we flip the whole fraction. Now, you do need to be careful about that. When you flip this whole fraction, nothing changes about these numbers. This will still be a 9, a y to the negative 4, and an x to the 6. Even though the y to the negative 4 is going to end up on top, we did not physically move it because of the negative 4. We moved it because of the negative 1/2. So your first step is, if you want to do this way, you just write 9y to the negative 4 over x to the 6. I just flipped the whole thing, and I changed this to a positive 1/2. Now we would take 9 to the 1/2, y to the negative 4 to the 1/2, and x to the 6 to the 1/2. So this is the square root of 9 times negative 4 times 1/2 would be negative 2, and 6 times 1/2 is 3. So this would be square root of 9 is 3, y to the negative 2 over x to the 3rd, and then we move the y to the negative 2 to the bottom. And I have a sick child, so this is going to be the end of this video. And we finished the last problem, so we're good.